Now that we've got a basic understanding of what a polynomial function looks like in standard form, and we can identify all the different types, we now need to move into working with the different ways of using these polynomial functions. And one of the things that we do with all functions is we learn how to graph them. Well, with graphing any polynomial function or any function type, we're going to have a shortcut method or some ways to shorten the process. But one of the things that you can always do to fall back on to graph any function is to simply create a t-chart and supply some values for x and then plug those values in and get the corresponding y value so that we have a point. Well, if you remember that we call this process of substitution into a function is called evaluating, and so you want to be very familiar with the idea of evaluating a function. And so we're going to just get some practice on evaluating a function with higher degree polynomials. Now you're probably comfortable doing this with a linear function and now so with a quadratic function, but this is going to take on a different level with higher degree polynomials. So we'll start with example number 2. Now you notice we have now identified the substitution method for evaluating into two different methods. And we'll start with the one that you already know, which is the direct substitution method. That's where we're taking what's given to us, in this case x equals to 3, and we're going to substitute it in directly for every single x value that is given to us. Now, to do this, it is not important that the polynomial is written in standard form for you to get a right answer. However, I would definitely recommend you getting in the habit of writing all of your functions in their standard form before you start working with them in any kind of format. So we can see here in this problem that we have evaluated f of 3. Now what I'm going to suggest to you, and this is important, get in the habit of doing this entire step with your calculator. That'll allow you to skip straight down to this part. The more you practice putting that in your calculator in one entry line instead of doing it in multiple steps, the less time that it'll take you to work these problems, and time is going to become a factor with these problems as they get longer and longer. Also, space is going to become an issue. So if we can in some way eliminate one of these steps with calculator use, then that way we'll take up less room in our paper and give us more time to think and more room to write. Now, what we've basically done here with this direct substitution is we've said that when x is 3, that our output value, f of 3, equals 98. And if you recall, f of x is the same thing as y. So we have basically created the point 3, 98. Now, obviously that's a long ways up the y-axis, but it is a point on this particular function. And so anytime you evaluate for x, you're receiving an output value that gives you a point on the graph. So keep that in mind. Now, we also have another method of substitution. It's called synthetic substitution. And while this may not be so important right now, this will be a very, very important process to you in the upcoming lessons. And so this is an appropriate place to demonstrate it. So let's take a look at synthetic substitution. What happens in synthetic substitution is we actually pull out all of the coefficients and work with just the coefficients and eliminate the variables. Now, in order for this situation to work, we must be working with every single coefficient. And what I mean by that is this. If you look at the original function, we are missing an x to the third term. So this is missing. It's not actually in there. Well, in order for synthetic substitution to work, it has to be in there. And so when we fill it in and it's not there, we give it a coefficient of 0. And so once we write this in standard form, which is required for synthetic substitution, we have everything lined up. We just simply are going to take all of the coefficients with their signs and drop them into this little situation here. Now, let me point out to you that these numbers would not be there, and so I'll work this same exact problem from scratch. And so we have 2, we have 0, we have -8, we have 5, and -7. And so this is what you'd be starting off with. And so we're just going to create a little box here to run our synthetic substitution. I'm evaluating this problem for 3. So I'm going to put the little 3 out here. And that's important because that's the number we're going to be using all the way across this in synthetic substitution. So the very first step for me is to just take this 2 and drop it down outside of the box. Now anything that we have below this line is going to be multiplied by our 3. So we're going to say 2 times 3. So 2 times 3, and we're going to put that number right back up here in the box. And so there's a little diagonal action here. So it goes down and then it goes back up into the box. And then we start that process over. I'm going to combine the 6 and the 0. So 6 plus 0 is just simply 6. Now that I have a number below, I'm just going to multiply that by the 3 and move that new number back up into the box, which is 18. And so you can see we're obtaining these numbers that we had here. Again, I'm going to go through the process of combining terms. Now, addition, subtraction, whichever way you want to look at it, you're just basically taking the numbers or the values that you're given and combining them. So negative 8 and a positive 18 gives us 10. Again, numbers down here, I'm going to multiply it times 3, move it diagonally back into the box, which gives us 30. Combine like terms gives us 35. Last time here, we multiply this times 3, move it up, and that simply gives us 105. The very last step here is to combine these terms, and we get a 98. Now there's nothing left to move it to, so we don't multiply this by 3, we just simply stop right there. Now, you can now see all of the numbers in this example and where they came from as we work that. Also notice that this 98 is actually f of 3 equals 98, just like it was back up here in direct substitution. So that is an example of direct substitution and synthetic substitution work getting the same answer. So let's go ahead and you take some time to work sample problem number 2. Use direct and synthetic substitution. Okay, so I'll start with direct substitution, and so we're going to evaluate this function at x equals to 4. So I'm going to say f of 4 equals 5 times 4 to the third power plus 4 squared. Notice I use parentheses. Even though I didn't have a negative number, I'm using parentheses all the way across for my substitution. Please get in the habit of doing that, especially when we start having negative numbers being raised to a power. That will be very important. Now, if you've shown me this part, then you can go ahead and evaluate that in your calculator, which should give you a value of 321. Now I'll do this in a direct manner. So first things I want to do is I want to look here. Do I have any variables missing? I have x to the third, x squared, x to the first, x to the 0. That's good. We always start with our highest exponent or our degree. We don't need to worry about a fourth or a fifth or a sixth, whatever. If the third degree polynomial is the highest, that's where we start. And so we take our coefficients, 5, 1, negative 4, and a positive 1, and you can see that I got that from each of these values here. And then I'll create my little box and I'll evaluate this at 4. So let's follow along here. I'm going to drop the 5 out. 5 times 4 gives me 20. I combine the 20 and the 1, gives me 21. 20 times 4 is 84. I combine those terms, get 80. 80 times 4 is 320, which gives me 321. And if you look at that, we had the same value that we had when we did direct substitution. Okay, so this is a new look at a way to evaluate polynomial functions. Let's finish up this lesson by taking a look at an example of a word problem that you could have to deal with. So what you may see, and this is just a basic evaluation of a word problem, but you need to kind of understand the parts and you need to understand what your answer should look like. And there are a few little things in here that are not so straightforward that you need to be familiar with. So let's take a look at what we're given. It says retail space in shopping centers in the United States from 1972 to 1996, and so that's probably going to be some very important information. can be modeled by the given function. You can see we have a polynomial function, third degree, with an s and a t. So we really need to be familiar with what the s and the t is representing, because they're going to have to give us some s, they're probably going to have to give us a t, or they're going to have to give us some information on what to find. And so it says s is the amount of retail space in millions of square feet, which means that whatever our answer is really implying that we've got this many zeros on the back end of it to imply millions of square feet. And t is the number of years since 1972, and that's another very, very important situation. So whatever year we're given, we don't want to put it in terms of the year, but we want to subtract that from 1972, or subtract 1972 from that year, so that we can get t in terms of years, not the actual year. So a couple of things going on here. Now keep in mind, if we get an answer for the s, the retail space, that is 1.0, what that's really telling us is that we have 1 million square feet of retail space. Conversely, if we got something that was like 20.2, that would tell us that we're 20 million and then 200,000 square feet, and so that 0.2 is starting those 6 spaces for the zeros. And so just to kind of give you a sense of what your answer might look like. So it says, how much retail space was there in 1990? Well, we're going to take the 1990, and we need to know how many years that was since 1972. And that's going to give us a value of 18. This is what our t is represented by. T is equal to 18 years. And so we're going to use that as our input value into this function so that we can figure out our s, which is our retail space. And so we're going to say s of 18 years, and then of course we're just going to fill in the rest of this and make sure you get the decimal places and the zeros correct. And then of course for t, we're going to put that in parentheses, and of course that's going to be 18. And so then we have negative 0.27 t squared. Again, 18's going in for the t, plus 150 t. And again, I'm using parentheses all the way through just to stay consistent. And then plus 1700. Now that we have this long polynomial, what I want you to get in the habit of doing is just punching this straight into your calculator. If you're having trouble getting the correct answer, doing this in one entry line, do it piece at a time. Make sure you get the right answer, but practice this and make sure that you can do this correctly before you try to do it on the test. So s of 18 is going to equal to 4272.86. And remember, this is in millions of square feet, so really we have six zeros that we need to add on to here. But keep in mind, this 86 after the decimal place is really already representing 2 of those zeros. So this is going to be 4272.860.000. I'll put commas every 3 spots. And so that's how many square feet of retail space there was in the United States in 1990. So this is a good example of how we could use an application problem to have to evaluate polynomial functions. A little bit more going on than your normal plugging in values, but you have the skills to do this.